In this video, we're going to be taking a look at standing waves in various tubes, and we're going to be solving for a couple problems with an unknown frequency and an unknown velocity. So if you take a look at these diagrams right over here, we have three different tubes, one with two closed ends, one with two open ends, and one with a closed and open end. If you take a look at these wave patterns in each of these are all various resonating frequencies that create standing waves. A standing wave is a phenomenon to where the waves are moving back and forth within that tube, and they are experiencing constructive and destructive interference. And at the very ends, they have things called nodes or antinodes. If it looks something like this, that's called a node. That's an area where all the energy is canceled out. And if it looks like this, then it's called an antinode. That shows the maximum amount of displacement or energy of that particular wave. Now, if you take a look at all of these different patterns, basically how they work is each of them have a certain amount of waves within the tube, which is going to help us in our problem solving and our conceptual understanding as well. When you take a look at each of these, I kind of call them eyeball shapes. So if you take a look at these eyeball shapes here, each one of these eyeball shapes is exactly half a wavelength. So if you kind of use that as your reference, then you can see how many wavelengths are within each different tube. So our first tube over here that has two closed ends has half a wavelength. This one is one total because it has two halves, and then this one is three halves. This one over here has a half of an eyeball shape, so that would be a quarter, and then another quarter. So this is going to be a half. This one over here is going to be one full wavelength because it has half a wavelength in the middle and then two quarters on the side. And then this one is going to be 1.5 because it has one full wavelength in the middle with the two eyeball shapes and then the two quarters on the end. So it's 1.5 total. And then for our closed and open-ended tubes, we have a quarter of a wavelength here because this is half of an eyeball shape that is half a wavelength. This one is 3/4, and then this one is 1.25. So here's the full one. The two eyeball shapes makes one full wavelength, and then again a quarter at the end. Now they have something called a harmonic for each one of these. For the one that has two closed ends, this would be your first, second, and third harmonic. And then once you go to the fourth one and fifth one, you're basically adding one more eyeball shape. For the one that has two open ends, it goes first, second, and third, and you're basically adding an additional little eyeball in the center here every time. And then your one that has a closed and open end only has odd harmonics because of the nature of having one node and one antinode. It can't produce any even frequencies, so it has odd harmonics. So let's go ahead and take a look at our first problem. We have a 44 centimeter violin string that's creating a sound that travels 344 meters per second. What is the frequency of this third harmonic? So we're going to be using our wave speed formula, velocity equals frequency times wavelength, and we are interested in finding this frequency as our final answer. So we already have the velocity of 344 meters per second. So our main goal is to find the wavelength. And if we can find the wavelength, then we can go ahead and do a little bit of algebra to solve for the frequency. So if it is the third harmonic, what you want to do is first identify what kind of tube you're looking at. And this one isn't exactly a tube, but it is a medium that is closed on both ends. So the way a violin works is where the bridge is, which is like the wooden part that pushes up the string, that is a closed end that doesn't allow any vibration, so that there's a node there. And then where you place your finger creates another node. So it's going to look something like this. Okay, now it's the third harmonic, so it's this one over here. So then that means that there's 1, 2, 3 eyeballs. Okay, remember each one of those eyeballs is 1/2. So we have 3 halves of a wavelength that is equal to 0.44 meters. Okay, so I converted that 44 centimeters into meters. So there's 1.5 wavelengths within that 0.44 meters. And then when you go ahead and divide both sides by 3 over 2, then we have our wavelength, which comes out to be 0.293. Now we can go ahead and solve for our frequency. We know that our velocity is 344 meters per second. We're looking for our frequency, and we know a single wavelength is 0.293 meters. So if we go ahead and divide both sides by 0.293, then we get our frequency. Our frequency equals 1174.06 hertz. Now for our second problem, we have a 30 centimeter organ pipe that's playing a 573 hertz note at its fundamental frequency. How fast are these waves traveling through the air? So the fundamental frequency is an additional term that you're going to want to know. The first harmonic for any of these tubes is also known as the fundamental frequency. And some additional vocabulary you're going to want to know on top of knowing the first, second, and third harmonic, or the first, third, and fifth harmonic, is then after the fundamental frequency, each one after that is also known as an overtone. So you can call this one the first overtone, the second overtone, and so on. So once you go to the overtones, that means the next resonating frequency above the fundamental frequency that creates a standing wave. So this would be the fundamental frequency for the open-ended tube that's open on both ends, and then this would be the first overtone, and this one would be the second overtone, and then so on. All right, so let's go ahead and take a look at our second problem now. We're looking for a velocity this time. So we're looking for the velocity, and we do already have the frequency of 573 hertz. So we need to make sure we find a wavelength to plug in. Now, it's the fundamental frequency for an organ pipe. An organ pipe is open-ended on both ends, so it's going to be this one right over here. So because it has a quarter wavelength here and a quarter wavelength here, there is a total of half a wavelength inside of 0.30 meters of pipe. If you multiply both sides by 2, then your wavelength equals 0.60 meters. Now we can go ahead and take that number and then plug it into here. And then if we do 573 hertz times 0.60 meters, then we get our answer, which is 343.8 meters per second. So the first thing you want to be aware of is the different types of tubes, whether it's closed on both ends, open on both ends, or has one closed and one open. You want to be familiar with the vocabulary of the different harmonics that are in green. And then also the other set of vocabulary in purple, where the first one is your fundamental frequency and each one above it is known as an overtone. And then if you know that within each of those tubes, if it's a closed end, there is a node, and if there's an open end, there's an antinode. And then each one of those little eyeball shapes is equivalent to half a wavelength. If you use that as your rule of thumb, you can figure out how many wavelengths are within each tube, and that's going to help you with this step right over here, with how many wavelengths are within that tube, and then this one over here as well, which was like the same step. That'll help you find your singular wavelength to plug in your wave speed equation, and then you can go ahead and solve for the velocity or frequency from there. So I hope that was helpful to you. Thank you for watching and listening.